All right, welcome back from the break, everyone. We're continuing with our theme of multi-messenger astronomy with a series of talks from different folks in the field. And we're going to kick things off with Kendall Ackley. Take it away.
Great. Well, thank you very much for inviting me here. It's my pleasure to, is it okay? Yeah, there we go. Yeah, okay. It's my pleasure to present today. I thought I would give a topic, a talk on a topic that I think has been my focus for the last few months, if not, to be honest, years, in terms of reducing latencies in real-time astronomy. And so what I wanted to do is preface some of the main challenges that we have in terms of gravitational wave optical follow-up. And so here we have that there are a variety of different sources here, particularly for optical astronomy, we're looking for neutron star mergers. These are going to be more rare than the binary black holes. We've learned that from Michael's talk last. But in particular, what I want to focus on is that there's this sort of evolving nature of these sky maps. So these are what we call probability sky maps for two different types of events. One is for a binary neutron star event. This is call number GW170817. This is probably the one of the most famous ones. It was about 28 square degrees. And the next sort of one of the more interesting events that came out of the latest LIGO observing run is one that's called GW230529. You can see that's pretty much the entire sky. In particular, within these sky maps, we're looking for transients that are fading very quickly, and these are over time scales of days. So here's 0, this is units, this is in days here. So over the past 10 to 15 days, we can see that it's decayed by quite a bit in the optical. It makes it very challenging that it's going to decay very quickly. And in particular, we also have a high level number of contaminants. And so this is the peak magnitude versus duration of days. And we're really looking within this region where we have a high number of potential lookalikes, so to speak. We call them contaminants, things that look similar. And so one of the ways that we tried to address most of these challenges is by looking at designing a wide field optical telescope. And so I'm going to be focusing on the gravitational wave optical transient observer. This is a system that I have helped to build from the ground up using sort of off-the-shelf components. It was meant to be modular. It's meant to be approachable. It's meant to be cost effective. And so this was proposed in 2014 as a dedicated facility. Its aim is to primarily go after gravitational wave transients and go after all of these gravitational wave alerts that come in. But I did want to mention that as with designing any sort of telescope facility, you have to have a trade-off. You can either choose your cadence, so how quickly you observe your field, how much area you collect, and how much flux, so how deep do you go in space. You can't have all three. You have to choose two. At least two. And so for GOTO, we particularly chose area and cadence. So I just wanted to preface this by saying that we went through multiple stage designs. So this was in response, we built this facility in response to LIGO and the gravitational waves and how the field has grown. We built the instrument over several staged prototypes from 2018 all the way to 2020. And just to highlight a couple things that we have the capability of doing 5-slot filter wheels, wide cover area bands. So this is a 400 to 700 nanometers. This is really wide. So in terms of looking at color evolution or the blue to red evolution of this particular transients, we're not particularly mindful of what that transition looks like. We just want to collect photons. Each one of these telescopes is about 5 square degrees, and we have the cameras for people who are interested. So since then, we are at full network capacity. We are observing nearly continuously every night. We have 2 antipodal sites. One is located in La Palma on the Canary Islands, which is off the coast of Africa. And we have another one at Siding Springs in Australia, which is pretty much in the outback. And so we survey the sky roughly every 2 to 3 days, and we're gathering about 2 to 5 terabytes of data every 24 hours. To compare with some other facilities that are online doing this style of search, here we can see the GOTO coverage. This is 2 by 44 square degrees. We have 2 domes, and each per site. So this is going to be on one site. This is the 2 kind of covers on La Palma, and we have another duplicate in the south in Australia. And so we can see here that it's sort of set up on this mount boom arm with these 8-unit telescopes that make up each of these 8 individual sort of image regions where, you can see roughly M31 there, Andromeda covering N1. And the reason why we chose to separate it over 2 domes is primarily because we can be more flexible. We can choose to either stack the images, look at the same part of the sky at the same exact time, or we can say, I want to cover more of the sky all at once. And so it's adaptable in that way. In operational mode, I just want to highlight here, this is the full sky, and in blue is what is coverable and observable by the southern node, and in red is the northern node, and in purple is the equatorial plane, which is roughly where both sites can co-observe with a small latency. And so we have about 800 tiles accessible per site, and we can observe roughly 500 to 600 tiles visible every 8 to 12 hours. And so basically this means that no matter where the gravitational wave alert sky map comes and how it sort of presents itself across the sky, we can target it nearly continuously from both observing facilities. Okay, so that's basically the general overview, but what I wanted to go through was more of the data flow and control and the latencies with that in terms of just how long does it take from getting the alert from LIGO into getting an image through our pipeline and processed and that candidate's identified. And so just a brief overview here, we're continuously listening for gravitational wave alerts. We also are listening for other events, things from gamma ray bursts, things that are similar in explosion, things that come in very quickly that we need to respond to. We have in our internal system, our Sentinel and our scheduler, we assign it a priority. We say, this is important, this is not important, either target it now or it can wait. Once this gets targeted, we send the commands to each of our telescope systems, and then depending on our internal strategy that we've defined for that particular target, we can say, okay, I want telescope 1 to primarily scan as much of the sky as possible, and telescope 2, I want it to focus on high probability areas, and I want it to sit on those particular fields. Or it can alternate depending on maybe one of the telescopes is offline, and so we need to borrow the second one to take over. Once the images have been taken, they are sent through to the image processing pipeline. They go through a raw transfer stage, and then we go through what we call the typical pipeline processing. So you take your image, you remove some of the noise sources that come in, things like bias backgrounds, dark noise currents, things like that come from CCDs. You take an old template that is very well calibrated, very almost noiseless as it can be. You take those 2 images, you basically subtract them, and out comes your transient. Once that transient pops out, we send it into what we call our GOTO Marshal, and we look for candidates in that way. A lot of this has been fully automated to this point, but I'll go through sort of the hidden latencies on.
A quick question.
Yes.
The image processing pipeline, is that low latency or that sort of offline?
So in this particular case, it is low latency, but I want to specifically mention what we might do for the later, longer latencies and what you could gain. So yeah, so
So at the moment, this is offline.
Yeah.
This is once you get the information from LIGO. LIGO has to do it quickly. You collect the information quickly, but then you take your time to do the processing at the moment.
We can, yeah, exactly. Okay. And I think this bears some further discussion. So I think that's a really good point. Yeah. Okay, so the telescope control. This was built primarily by a colleague, Martin Dyer, who runs. It's fully autonomous. So we're listening continuously for these alerts. We receive the alerts. These are called VO event notices, or what they call GCN, gamma ray coordinates network notices. We come in, we listen to them, we parse them, and then we have multiple daemons using Pyro to communicate with the different hardware. So we say an observatory has come in, schedule it for these different telescopes at these particular times, and then pass it off to what we call the pilot. And so this monitors, various systems about whether or not we need to control the mount, the power, the different interfaces, and then what we do is we can get some feedback results. And so So this is just how it's powered for the telescope control. The scheduling and strategy. So this is monitored by what's called the Sentinel. So this is alert monitoring. It receives external events and it produces the priority and follow-up event. We take each one of these gravitational wave sky maps, we map them onto the all-sky grid, and then we assign it a priority. And we follow some logic based off this, which is based off the properties of the event itself. So whether does it have a particularly low false alarm rate, target that. Does it have some probability of it being astrophysical below some certain value, or is it close enough, target it as such. Once that's done, it passes through what we call the CADMLO. So this is the automated pipeline. So once the images are taken, we call these the raw exposures, they're transferred over to Warwick. We're doing about 0.25 petabytes of raw data per year being transferred over. This is about 1 petabyte processed data per year. And we do what's called a rolling storage model for image level data. So as we are nearing our capacity, we decide which of the fully processed data do we need to release, always maintaining that we keep the raw images constant. Okay, and this is scheduled through various systems, primarily orchestrated through Apache Airflow. Okay, once we do that, the candidates have been identified. If there are any candidates, they get processed in the images and they get sent to what we call the Marshal. And so this is a web front end where we have our science image, we have our template, and then what you can see here is an image, a subtracted image with the transient in question. And so this was discovered just a few weeks ago. And so you can see the manual vetting delay is rapid, but I did want to mention that all of these numbers are going to be given in terms of medians, but the latencies are always going to be in these tails. And this is the area that I'm focusing on, is how do we reduce those tails? Okay. There's another stage that all the latency has to go to. So not only do we get potentially interesting aspects of the candidate, that a candidate has arrived, it has these properties, it's associated with this galaxy. But even with this single detection, what you can do is you can do a probabilistic association to say from a single data point, associate that transient with a galaxy, take that galaxy's redshift associated with the gravitational wave distance, then you have a localized volume. Then you can say, should I target this or not? And this is, again, a relative ranking. So this is the score. And so this is for AT2017 GFO. That is the counterpart to GW170817. That is the top ranked item that came out. It only gets a stronger association, potentially, once you add in the true false alarm rates. But to get to that, you have to understand your data set fully. We also have a system, once we've identified something is probabilistically interesting, we go to what's called the GOTO auto trigger, the GOAT. So this is fully autonomous identification of targets. It runs through an API, and we basically say this particular transient is interesting, send it off to what we call the Liverpool telescope and get either further imaging or spectroscopy. And with the auto trigger time lags, you can see roughly along these time scales and their particular breakdown of what candidates are returned. Okay, and I just want to highlight, the main science goals for GOTO is gravitational wave follow-up. So I just wanted to highlight some of, I guess, what we performed during 04 and how those latencies kind of manifested themselves. So here is our 04 prospects. So during the 04 run, we received and processed through our systems over 5,400 super events. 29 of those were retracted. Of those, over the full run, 255 events were considered to be significant, and that's basically a flag that says it is below some false alarm rate threshold. Of those, due to weather, scheduling, other different processes, we have targeted observations of 163 of those events. What this looks like in practice, so this is over the full 3 years of 04. We have our observing run and basically our latencies from the first alert to when we get in our first observation. We rolled over various strategies, and it was updated strategies. It'll be out in the paper that's coming out. But basically, we started to target slightly different events as 04 went on to try to target specific aspects of the physics. But we still maintained a rough median of about 3-ish hours, depending on the source, over the 04 run between getting our first observation. in the absence of having things immediately observable, what you can do is you can fill in the gaps. And so this is what we call serendipitous coverage. And so I can say, okay, we specifically targeted these 163, 162 events, but we are also continuously observing all the time, right? We don't know the physics, the sky maps, they change. Sometimes they can, different noise properties can be removed from the data, so you can tune your data set, improve the signal to noise ratio, improve different parameters, and you can have different sky maps completely. And so what we wanted to do is we wanted to address both the operational challenges of follow-up, but also that the gravitational wave sky maps themselves are evolving over even hours to days. And so what we do is we then cross-match all of our observations over your time window. And we basically try to maximize our field coverage over that time span, over from up to 7 days. And with that, we actually end up getting coverage with at least one image over almost the entire data set, which I think has significant physical implications. But what you can see is that this latency has increased significantly. So while you do get the physics of your time region is going to be shifted out. So that changes what sort of physical models you're able to target. Okay, and just sort of roughly end to end, what we have is we have about 35 seconds from when LIGO is triggered, a gravitational wave event, to when it produces the alert. So it's about 35 seconds for our sub data set, not for the entire data set. Of that, between the alert to the first observation was about 182 minutes. It takes about 10 seconds to transform the data from either Siding Spring or La Palma to our Warwick data center. It takes about 200 seconds to fully process that image all the way through to difference imaging, and then to get it to the Marshall. So from the first observation all the way through to that Marshall front-end page where we can say, is it real or not? It's about 900 seconds. Obviously, there's a lot of heavy processing tasks that are handled in here. Sort of the main components are built in, but where is all of that hidden latency, right? So what is actually component? If you sum these numbers up, you're missing a huge chunk. And so this hidden latency actually comes from sort of what I've identified are these types of flavors, right? So scheduler deliberation, how long does it take the scheduler to say, go for this? We have stale observing queues. Maybe the observing queue doesn't quite know where to go next. So it might be 1 or 2 seconds, but over 12 hours, it starts to add up. Weather seeing propagation, there's temperature fluctuations, humidity is rolled in. We need that humidity to leave out, and maybe our timing of our checks at 5 seconds, 10 seconds, maybe that's too long. We also have image QA latency. I think this is a main point that I specifically wanted to focus on. In terms of evolving gravitational wave information, a part of our sky map is no longer covered. Our machine learning algorithms have drifted. Subjective humans are in the loops. All of these will have physical implications. In particular, here's one potential set of models. This is one particular event towards the end of the 04. You can see that there's this gap. This is what we targeted, and then a couple of days later, we came back due to weather. But which part of these physical models are most appropriate? And you can see here in these blue kind of scatter points is our raw data, and in the oranges are stacked. So what images should we stack together to go deeper? We don't need to do that for every image, especially down here. We don't need to waste computing resources to do that. We probably don't need to do it here. We didn't get any physics. Where's that fine line? So just this is the last bit that I have here. This is the responsive QA system. So this is trying to address that the maximal data latency that you will achieve is by just true loss of data. So data that is completely unusable. And so it's to try to stop that latency from getting through your system. And so to stop data from progressing all the way through to find out that, of course, it's unusable. And so we have what I'm calling a middle manager. It's a canary. It's saying something's gone wrong with the data. Either your filter wheel has slipped, send a command back to the telescope. Don't even pass it onto the pipeline. Tell the telescope to recorrect. The shutter hasn't fully closed. Power cycle the camera. Moon glare, move the mount. Other things like bad tracking, bad seeing. Don't even bother continuing to observe under bad seeing conditions, etc. And so you can see here roughly, there's models. I didn't have time to go through them, what's kind of underlying these, but here you can see that this particular image is really cloudy, muffly, and you can see the jump in this global background. So it's very obvious to sort of catch these things in real time. And then to go further to catch the even sort of the tail end of the latencies requires a little extra effort that I'm hoping some discussions in terms of modern methods we can explore this. Yeah, so I think with that, I just wanted to summarize that, you know, there's a lot of data that was processed for this, but there's so much I think that still needs to be optimized, calibrated. How much data do we keep now? Do we basically assume that we filled in all the gaps, wait for LIGO to come up with candidates within their noise sources? There's a lot of things that I think that we should address by even just this facility as we continue to progress to these other facilities in the future, you know, in the next decade or so. I just wanted to say thank you very much for your time.
All right, questions for Kendall?
Hi, Kendall. So I'm not understanding. So these telescopes are optical telescope, right?
That's right.
And most of the events we observe are binary black holes, so they don't have the optical counterpart.
That's right.
So I don't know how do you improve that efficiency? Like I did not understand this part.
Yeah. Okay. So that is a good point. So one of the things that I wanted to mention is we particularly avoid binary black hole events. And so of the 5,000 events that came through, you're right that some of them, majority of those are going to be binary black hole events. But I think I would say a higher percentage of those are what we call terrestrial events. And those we wanted to target specifically. Well, at least, you know, this was something that I pushed through because I thought there is a low probability that there could be something interesting in that data set, but in the off chance that there is a genuine counterpart in that noisy data set live in low latency that has come from LIGO, we should still try to observe it. And what we end up getting is, in any case, this was just one thing, in any case, you still get transients and you can still do transient discovery even in this operational mode. So why not specifically target high cadence, rapid observations of even potentially, you know, junk terrestrial noise candidates.
And your goal is to learn from this and then use other observatory for the same, like sends alerts to those.
Yeah, so we would call ourselves a feeder facility. So we basically try to observe as much of the field as possible, gain transients, and then pass those off. Yeah.
Okay, thank you.
All right,
Thank you.
thanks. Other questions, Marone? And then we have a couple more.
If I understand correctly, you would like to reduce the latency from taking the image to the where you think where you feel you can take help, or where is something that obviously we cannot control the weather.
Right.
So if the weather is bad, but where do you see an opportunity to have impact there?
Yeah. Thank you. That's a good question. In my opinion, I think it's that a reality of so much of these observing that kind of gets buried in the noise is that so much of the data that comes out of facilities is unusable. Whether it's just noisy data improperly subtracted. And so if you can prevent that from getting through your system and actually make sure that
So early detection of
and that the data that
bad data.
Yeah, the data that you're putting in is of good enough quality.
So you are spending too much time on bad data.
That's right. Yeah.
So what prevents you from doing a quick filtering of the data as it comes in?
Yeah, so that's a lot of what this work is. So this was just a brief overview.
Right.
Just trying to capture it. But what I will say is that this is challenging in and of itself because if you do this, what I would consider proper, you're adding way more latency than just over process that data. You have to sort of do the quick filter checks that get the majority out, but you're still sort of losing it. And so are there methods within that to help without over?
So how quickly, so the question is how quickly you can get the sense that
Yeah.
that the data is not good,
That's right. Yeah.
because that is an overhead that you have to pay for.
Yeah.
So now there is an approach of speculative processing in hardware that you say, let's assume that the data is good, but also I would check whether the data is not good,
Yep.
and I will go in parallel.
Hmm.
And then if I conclude that the data is not good, I will stop, because hopefully I can do it sooner.
Yeah.
I don't know if it will help you, but because if the data is not good, you want to quickly retake it, right?
That's right. Yeah.
That's that. So
Yep.
maybe I don't know. It's just a naive thinking of saying I will not assume it's good,
That's right.
but let me move as if it's good, but I will check
Yeah.
for the other one. So is
Yeah.
that a capacity issue, or is that
It's
just a program? I don't know.
yeah. Yeah. I think at least from my perspective, it's more because once that image is transferred, we move on to the next field. So it's before the image gets transferred, can we stop it? Can we tell the scheduler to redo it? And all of that, you have to send the commands back. So that adds latency to fix whatever issue is shown up. Then you also have to tell the scheduler to reobserve it. Is that even invisible still?
Yeah,
So there's a lot of things to consider. It's
maybe we
yeah.
can get the scheduler out.
Yeah.
In any case,
Yeah.
that I'm happy to discuss it offline and see whether we can make it work.
Yeah, great.
All right, I
Yeah.
want to let Kurt ask his question and
Yeah.
then we'll get ready for the next speaker.
I'll go quick. Kurt from the Institute for Astronomy.
Right.
And I think you answered
Yeah.
one question, which is you're performing a optical transient survey when there's no triggers, right? So, and then a comment, which is, it strikes me that periodic restacking of your sky template is a good opportunity for OS pool.
Yep.
Because that
Yep.
is absolutely a high throughput computing job.
Yeah, exactly. Yeah.
And also FYI, we're working on roboticizing or automating spectroscopic follow-up. So a GOAT trigger to some of our resources would be appropriate. So my question is, can you give an estimate of your latency? It was not mentioned at the end of your latency slide to the GOAT trigger.
Yes.
To something that we could do.
Yes. So this would be, so this was the auto trigger time lag. So this was cumulative fraction. So it's roughly it's about 10 minutes.
So roughly 10 minutes.
Yeah.
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 All right. Thank you.
Yeah.
All right, thank you, Kendall. That was great.
Yeah.